Hi everyone. Today we're going to teach notes 5.2, which has to do with sum and difference formulas. All right, before we get started, I do just want to reiterate some things that we might already remember. When we see the word sum, we want to think addition. And when we see the word difference, we want to think subtraction. All right, so before we get started, I want you to have your golden ticket with you, okay? I understand the formulas we're going to use today are technically on these notes, but I want you to also know that these are given to you on the golden ticket. So if you go to the side that's trigonometric identities, on the bottom left corner, you'll see the sum and difference identities. Those are the exact same formulas that we have on our notes today. So if it's on the golden ticket, just remember it will also be on your golden ticket for your test, so you do not need to have these memorized. Okay, just want to get that out there before we get started. Well, when we start solving for sum and difference formulas, okay, remember I told you the key here in this entire unit and the rest of trig is to have the unit circle memorized. So in order to use any of these formulas that are listed, we need to choose angles. We need to choose angles that exist on our unit circle. Okay, so for example, we can't choose the angle 1 degree because 1 degree is not on the unit circle. We can choose 0, 30, 60, 45, 90, 120, 135, 150, 180, and so forth. Okay, any of those angles that are on the unit circle we can use. All right. Also, if you do find yourself needing a random angle like 5 degrees or something like that, chances are you're just choosing the wrong angles. Okay, every single problem that we give you can be established, can be created through angles on the unit circle. It's just a matter of you choosing the angles you would prefer. Okay, so go ahead and look over these formulas. One thing I do want to point out is the sum and difference sections. Okay, so in all three of them, they have the option to add or subtract. Okay, and that symbol on the left is a lowercase a, we call that alpha. And then the symbol on the right is a B for beta. So if I ever say alpha or beta, that's what I am referring to. Okay, what those A and B stand for are just angles. Okay, so if I have something, and we'll talk about it in our notes, if I'm adding the angles 45 and 30 together, 45 would represent angle A or my alpha, and 30 would represent angle B, which would be my beta. Okay, notice how if we take a look at sine, let me zoom in here. When we take a look at sine, if I were to just focus on the addition, okay, the addition part up here. If addition was what occurred on the top in my formula on the left-hand side, I want to choose the same top one on the right-hand side. Okay, so just keep in mind, keep your tops and bottoms together. So I want to say that because take a look at cosine. If you were adding your angles together, we would choose this option here up top. But when we go to use the formula, it's no longer addition, it's actually subtraction. Okay, I just want to point out the differences now so that we don't get confused later. Just because I am performing what's called the sum formula on this one, if I were to be adding the angles together on a cosine, doesn't necessarily mean I would still be adding them in my formula. Okay, the formula is established in a way to where you have to match the pieces. So whatever was on the top to begin with, you're going to use on the top throughout the same formula. Okay, take a look at tangent. Let's do the same thing. If I'm talking about adding my angles together, when I look at the numerator, I'm going to add in the numerator, but when I get to the denominator, I'm going to subtract. Okay, so match your tops, match your bottoms together. That is what I want to get out of this. So maybe make a little note here. Match tops. Let me spell that correctly for you guys. match tops and bottoms together. Okay, that little reminder there is not on your formula sheet, so just keep that in mind when we go to use those later and if we don't have that reminder in there for us. All right, so let's get started on a few examples here. We got what? 5, 6, 7 of them? Okay. So example 1, it says find the exact answer using sum or difference formula. You're allowed to add or subtract, whichever one you feel more comfortable with. If I'm being completely honest, I like addition more than I like subtraction, so I try to shoot for addition first. However, when we get to question 1, it's saying cosine at 15 degrees. Okay, so I think about my angles and I'm like, well, I can't really add any two angles together to get 15 degrees, but I know I can subtract angles to get 15 degrees. All right, and one little thing I want to say is you can choose any angles as long as they're on the unit circle, and as long as they can get that 15 degrees, whether it's addition or subtraction, you can choose any angle. Okay, so when I go through these notes, and if you try working ahead and you choose different angles than what I did, just make sure that our answers match at the end. Okay, there's no right angle to choose at every single term or every single time. We can choose whichever angles as long as it still adds or subtracts to the number we're trying to get. So here's how I'm going to start. I'm trying to get 15 degrees. So I'm going to use a difference formula because I know that I can subtract two angles from one another and get it to work. So I'm going to choose the angles 45 degrees and 30 degrees because I know that 45 minus 30 does in fact get me that 15 that I wanted. All right. I'm talking about cosine. So I'm going to reference the cosine sum and difference identities on my golden ticket or up above on my notes. Again, I'm using the difference here, so I'm going to choose the minus version. So I'm going to say cosine of 45 degrees minus 30 degrees. And I'm going to fill in every single thing on that formula. So I'm just going to fill in every A that I see is going to represent 45. Every B that I see is going to represent 30. So just to reiterate, my alpha here is 45, my B is 30. So I'm going to just fill in the formula, swapping out my alphas with 45s and my betas with 30s. See, and I already messed up there. We want addition here, again, matching my pieces. Subtraction is my difference formula. Difference is at the bottom, so when I go to use my formula, I want to use addition because that is what is on the bottom. So all I've done is just replaced every alpha with 45 and every beta with 30. Okay. From here, I know my unit circle. So I'm going to take my values from the unit circle. If you need the unit circle with you, please take it out and have it nearby. Otherwise, you can use it from memory as it should be memorized. And I'm going to swap out every single one of these values for their respective piece along the unit circle. So cosine at 45 degrees, if I were to find that, it would be the square root of 2 over 2. Cosine at 30 degrees would be the square root of 3 over 2. Sine at 45 can get swapped out with root 2 over 2. And sine at 30 can get swapped out with 1 over 2. All right, now we went from the formula down to the coordinates. Well, just to reiterate, the formula is using multiplication in between these pieces. So now I get to take those fractions and multiply them together. Remember the rules with multiplying square roots. If both numbers are inside the square root, I'm going to multiply both numbers only inside the square root. So the first fraction is going to turn into the square root of 6 on the inside. Denominators also get multiplied, so I have over 4 plus square root of 2 times 1 still leaves me with square root of 2. 2 times 2 leaves me with 4. All right. From here, they have the same denominator. So we can actually go ahead and do one more added step. Whenever they have the same denominator, I can combine both fractions. Okay, keep in mind both of these radicals are different from one another, so I can't combine them to make it a square root of 8. I must keep them separate. Square root of 6 plus the square root of 2, but I have all over 4. And that will be my answer. Okay. Again, if you chose different angles and you got root 2 plus root 6 over 4, that can also count as an answer. Okay, remember addition allows us, the commutative property of addition allows us to switch out our values. All right. So when we get to question 2, the beauty of radians is that we can always convert to degrees. All right, so notice that sine 7 pi over 12, that's in radians. Right off the bat, can you think of two angles that add up to give you 7 pi over 2, or even subtract to give you 7 pi, not over 2, over 12? Okay, the fact that these are radians really confuses not only you guys, but also me, okay? So if you need to, there is absolutely nothing wrong with converting these to degrees, okay? Take a look at the answers that we end up getting anyways. Okay, we don't get answers that are like radians or answers that are like degrees. So it doesn't matter what we use in our work as long as it all works out at the end. All right. So what I would recommend when we see these radian values, immediately swap it out with a degree. Okay, so that's going to take some background knowledge. How do we go from degrees to radians? Well, I want the radians to cancel, so I'm going to put them in the denominator. And I remember that 180 matches with pi. So when I type that into the calculator and I simplify my fraction, my pi's will cancel, and I have 105 degrees. So I'm really working with the question sine of 105 degrees. Same exact question, but now instead of radians, I have degrees. All right. So I can choose either the sum formula, so I can add two angles to get 105, or I can try to use the difference formula and subtract two angles to get 105. Either one is going to work. It doesn't matter if you like the addition or if you like the subtraction, all right? But like I stated at the beginning, I like to use addition as much as possible just because for whatever reason, addition just makes more sense to me. I see it before I see subtraction. That's honestly what it is for me. All right, so I'm going to use addition. And the two angles that I'm going to use, again, from the unit circle are 60 degrees and 45. So based off of this, 60 represents my alpha, 45 will reference my beta, okay? Doesn't matter which order I put them in, if I put 45 or 60. No, okay, either one is still going to give me 105. The only difference is you would be referencing different parts of the formula. So if you do 45 and 60, make sure that 45 would reference your alpha while 60 references your beta. Okay, there's nothing wrong with that. So I'm going to copy down the formula for sine, again, the sum of sine. And every time I see an alpha, I'm going to swap it out with 60 degrees. And every time I see beta, I'm going to swap it out with 45. Getting to my identity, I'm using the sum formula. Sum was on top, so as I keep going through the formula here, I'm going to keep a plus in my work. Okay. And now I'm going to use the unit circle to help me. So sine at 60 degrees is going to be root 3 over 2. Cosine at 45 will be root 2 over 2. Then we're going to add cosine at 60 degrees is going to be 1 over 2. And sine at 45 would be root 2 over 2. Go ahead and multiply these fractions again. We have root 6 over 4 plus root 2 over 4. And then we can combine both fractions to get root 6 plus root 2 all over 4. Again, doesn't matter which order, you could put root 2 plus root 6 all over 4. That would also work. All right. So again, whatever angles you chose, if you didn't choose 60 and 45 and you chose, oh goodness, I don't know off the top of my head right now. If you chose even subtraction with some angles that would work, 150 and 45, okay, those are both on the unit circle. If you chose subtraction, just make sure our answers at the end would match, okay, and they should. So I'm going to go into tangent, okay, and for some of you, we talked about this last class, and I said, well, there's what's called a messy tangent, okay? What the messy tangent is, if you remember your unit circle, if I ask you for the tangent at 30 degrees, you would say root 3 over 3. But originally, if I were to find tangent at 30 degrees and do sine over cosine, I would get root 2 over 2 divided by root 3 over 2. Again, this was at 30 degrees. Sine over cosine. I would then skip flip multiply. My 2's would cancel. Oh, sorry. Sine at 30 degrees. Sorry, guys. Was 1. I was like, that's not right. Okay. There we go. 1/2 divided by root 3 over 2. Still skip flip multiply. My 2's would cancel, and I'd be left with 1 over root 3. Okay. But we don't like square roots in the denominator, so we would have had to simplify that. And that is where I got root 3 over 3 from. This whole process is what makes this a messy tangent. All right, so from here on out, whenever you see root 3 over 2, or excuse me, root 3 over 3, you're going to know that that's in reference to a 30-degree reference angle for tangents. All right. On this section here, when we use sum and difference angles, if we have to use a 30 or 60 reference angle at all, we need to steer clear of any 30 degrees. And the reason we're going to steer clear of those is because we're going to have that mess to work with. And we don't want that mess to work with if we can prevent it. All right. So that is what this rule here is for, preventing the mess. All right. And again, if you remember the 60-degree reference angle for tangent, well, tangent at 60 degrees is just nice and simple square root of 3. There's no fraction. There's no simplifying the denominator. There's none of that. So it makes it much, much easier for us. Okay, so that is why that note is there, to stop us from doing more work than we need to, and just causing more confusion in the end. All right, so with that note in mind, I want to find some sort of sum or difference of two angles that are going to either add to 285 or subtract to 285. And again, I like addition. It's what I prefer, so I'm going to use addition. It tells me to use a 60-degree reference angle, so no matter what, I'm going to add 60 degrees. And I'm just going to put it there because it matches my teacher notes. So the other angle, if I was adding, my other angle would have to be 225. And again, on this procedure, make sure you're choosing values that are on the unit circle. So double check, make sure 225 degrees is in fact on the unit circle before we continue. It is, so we are good to go. So here's my alpha, here's my beta. I'm using the tangent identity this time, and I'm doing the addition. So matching all of my top pieces together. So I have tangent at 225 plus tangent at 60 divided by 1. Again, same pieces. So instead of adding in the denominator, it now tells me I want to subtract tangent 225 times tangent 60. All right, let's clean this up. Remembering tangent 60 is root 3. Tangent at 225 is a 45-degree reference angle, which is the best tangent there is because it's always gonna be 1. If it's ever a 45-degree angle, we're always talking about 1. So tangent at 225 is gonna be in the third quadrant. 225 is in the third, which means tangent is positive. So I'm looking at a positive 1 plus tangent at 60 degrees would be a nice root 3. Okay, again, if we chose a 30-degree angle, that would make that a fraction right there. We don't want more fractions than we need. That's why we're going to steer clear of that. Denominator tells me to do 1 minus tangent at 225 again, which was 1. Tangent at 60, which was square root of 3. Clean it up a little bit. We're going to have 1 plus root 3 in the numerator, 1 minus root 3 in the denominator. Okay. This answer is good. It's not the best. We still need to clean it up. We still have a square root in the denominator. Okay. This one means we have 2 terms in the denominator. And whenever we have 2 terms, when we're trying to clean it up, we have to multiply by what's called the conjugate, for those of you that might have forgot. The conjugate tells you to multiply by the opposite of that radical so that you could cancel them out. So instead of doing 1 minus root 3, I'm going to say 1 plus root 3. And keep in mind, whatever you do to the bottom, we also need to do to the top. And again, this was my conjugate. Okay. So now let's just do a quick distribution. Numerator will turn into 1 plus root 3 plus another root 3, so that gives me 2 root 3. And then the last one, when I take the root 3 and I multiply with another root 3, it's going to give me the square root of 9, which does in fact simplify to just a plain old 3. Down in the denominator, 1 times 1, 1. 1 times root 3, I'll just write this out for you, positive root 3. Negative root 3 times 1 is negative root 3. And negative root 3 times root 3 would give me a negative square root of 9. Just letting you guys see where I'm getting these values from. Simplify the numerator here. I can combine that 1 and 3 to give me a 4 plus 2 root 3. Denominator, my root 3's are going to cancel with each other. And the square root of 9 will give me a 3. But I still have that negative in front. So now I'm looking at negative 2. When I simplify. I have a fraction. I am still allowed to clean this fraction up, paying attention to just the whole numbers or the number outside of that square root. All of those are in fact divisible by negative 2, so I can simplify this one more time to be negative 2 minus square root of 3. Okay, again, if it came out this way, you could also say negative root 3 minus 2. That would work as well. I prefer to put the number first and then the square root, just because that looks a little bit cleaner to me. All right. Let's try question 4. Again, anytime you see a tangent, we always want to use a 60-degree reference angle. Okay, always steer clear from the messy angles if we can. So let's do 255 for tangent. Again, I like to do addition. Actually, in this time, I guess I do subtraction, which I guess makes sense. Okay. If I originally did addition for 60 degrees, I'll just show you kind of my thought process here. I would say, well, what angle plus 60 would give me 255? That angle would be 195. Yes, 195. Okay, which would be great, but remember, it has to be on the unit circle. So is 195 degrees on the unit circle? No. So I'm not able to do that option. However, I can try subtraction, see if that one works. what angle minus 60 degrees would give me 255, and that would be 315. Check and look if 315 is on your unit circle. It is in fact on your unit circle, so you can use 315, okay? Now another thing, you don't have to use 60 degrees verbatim, so you could do 120, you could do 240, okay? They're all variations of 60 degrees, they're all reference angles of 60, which is fine. I just like to use 60 because it's just a pattern that I like to stick with if I can, okay? It works more often than not. So I'm going to use the difference formula for tangent on this one. So I'll go ahead and start my equation. 315 minus 60. Again, 315 is my alpha, 60 is my beta. Using the formula from my golden ticket or the top of my notes, I got tangent at 315. And I'm subtracting in the numerator. Tangent of 60, remember matching your pieces. But when I get to the denominator, I'm going to add. Okay. Clean up the pieces straight from the unit circle. So tangent at 315. 315 is a 45-degree reference angle. It's in the fourth quadrant. Tangent is negative in the fourth quadrant, so that gives me a -1. Tangent at 60, just like last time, is going to be the square root of 3. The negative that I had in my formula is the same negative I brought down there. Okay, so tangent at 60 is still a positive root 3, but because there's a negative in front, that's where the negative came from in the formula. Plug in everything else in the numerator there. Clean it up a little bit before I start going into my conjugate. And I have 1 minus root 3. All right. Clean up the denominator, so I need to multiply by the conjugate, which is 1 plus root 3 to top and bottom. Remember, we're multiplying. Numerator will become -1 minus root 3 minus another root 3 minus 3. Remember your steps in multiplying square roots. Don't forget those. Denominator, we have 1 plus root 3 minus root 3 minus 3. Remember, the whole reason we do this step is to clear out that square root in the denominator. If you don't cancel out that square root, something went wrong. So here we go. Cleaning it up one more time. Combining our like terms. -4 up in the numerator. Minus 2 root 3. Root 3's cancel in the denominator, leaving me with a -2. Last thing I get to do is take a look at all those values in front of the root, see if any of them are all divisible by -2, and simplify one last time. And I got 2 plus the square root of 3. Remember, your symbols will change, so keep track of that. All right, so far so good. Now let's say I don't just give you the angle. What if I give you information where we have to figure out some things, and I ask you to use specific identities? Okay. So before we can get started on questions like this one, we have to build what's given. We have to build those triangles, just like we did last semester when we built those SOHCAHTOA triangles, those right triangles, okay? That's what I'm going to do here. So I'm going to start with this bit of information first. Sine of alpha is 12 over 13 in quadrant 2. So I'm going to build my XY coordinates. Quadrant 2, I'm going to build a triangle. Remember, we're always referencing the angle closest to the origin. This is referencing alpha, so I just want to label which one's which so I don't forget. Okay. Sine is always opposite over hypotenuse. So from alpha, I'm going to go to the opposite, which is 12, hypotenuse 13. While I'm working on this triangle before I get to the other one, let's go ahead and find that third side. Don't forget Pythagorean theorem. We are working with a right triangle here. A squared plus B squared equals C squared. 12 squared plus B squared equals 13 squared. Working with 144 plus B squared equals 169. Subtract 144 to both sides. Gives me 25, so I'm looking at a B value equaling 5 when I square root both. So that's fine and dandy, but don't forget the detail that when that 5 gets placed there as your missing side, it's representing your x, and your x is in fact negative on that triangle. Okay, now I can go into beta. Beta is drawn in the first quadrant, so I'm going to do the same picture, but now I'm going to be in the first quadrant, labeling this is my beta triangle. It gave me sine again, so there's my opposite, there's my hypotenuse. Opposite is 3, hypotenuse is 5. This is a 3, 4, 5 right triangle, or we can solve doing the Pythagorean theorem. We should get 4. 4 is a positive on this one because we are in the first quadrant, so it represents my x. X is positive. So now that I have these two triangles created, I can start doing my problems. All right. So the first one tells me to do cosine of alpha plus beta. Well, these values aren't from the unit circle. They are now from the two triangles I just created. So I just have to find my cosines and my sines, or my alphas and my betas, in reference to whatever is necessary. So here's how I'm going to begin. It says find cosine of alpha plus beta. So I'm doing the sum identity of my cosine. I'm going to copy down that formula just so I can remember what I'm taking care of first. It tells me I need to subtract my sine of alpha and my sine beta. From here, I would go to my unit circle and I would take the values that I know. But we don't have a unit circle this time because we're not using exact angle values. Okay, I'm going to use the values from the triangles. So when I get to the first part that says cosine of alpha, I'm going to go to my alpha triangle in the second quadrant. That's why it was important we labeled which one was which. And I'm going to find my cosine of that triangle. Cosine is always adjacent over hypotenuse. So in this case, my adjacent was -5, hypotenuse 13. Then I'm going to go to cosine of beta. So looking at the beta triangle, I'm going to do the first quadrant. So my adjacent there would be 4, hypotenuse 5. Now I'm going to do sines of my alphas and my betas, which is nice because I could do this one of two ways. They gave me the triangle already. They told me what sine of alpha was and what sine of beta was. So I could do a quick just, oh yeah, that's what they told me from before, and just plug them in. I could also look at my triangles again, just like I did for my cosines, and take them there. Either way, they should be the exact same. So whether you want to take it from the original problem or from the triangle, they should be the same regardless. All right. Now let's simplify. Fractions when multiplied, you're just going to multiply straight across. -5 times 4, -20. 13 times 5, 65. Minus, numerators again. 12 times 3, 36. 13 times 5, 65. Okay, so same denominator. Let's just go ahead and combine these. -20 minus 36 more gives me a -56 over 65. I'm not able to simplify any further, so I will stop there. All right, practice, practice, practice. I'll let you guys go ahead and try B on your own. Again, you have my teacher notes as a reference, so go ahead and try that and check my notes if you need to. I am, however, going to do the tangent one with you guys, referencing the same triangles. Remember, question 1 has the same information, for all three parts. So the fact that I have this triangle already made, I can continue on for question C. All right. So I have tangent of alpha minus beta. If I look to my formula card there, it tells me I want to do tangent of alpha minus tangent of beta divided by 1 plus tangent alpha tangent beta. Remembering tangent is opposite over adjacent. All right, let's fill in what we found on our triangles here. First one, alpha. Tangent and alpha. Looking at my second quadrant, tangent there would be, 12 over negative 5. Just want to be sure. Yes, 12 over negative 5 minus tangent of beta, which would be 3 over 4, divided by, again, we are working with lots of fractions here, but that's okay. We will get through them. 1 plus tangent of alpha again, which we said was 12 over negative 5, and tangent of beta, positive 3 over 4. Okay. Before we worry about all this mumbo jumbo, let's just worry about the numerator chunk and then the denominator chunk. Okay. So in focusing on the numerator, look at the common denominators. They both need to have a 20 in common. So I'll swap those out, making this a 48 and a 15. Negative 48 minus 15 more gives me negative 63 over 20. I just took this negative here and just put it up top. You can do that. Denominator. Let's see here. Let's multiply this. So I'm looking at 1 minus 36 over 20. Getting the same denominator here, which means I want a denominator of 20. 20 minus 36 gives me negative 16 over 20. Now I have a fraction over a fraction, so I'm going to skip the first fraction, flip the second, and I'm going to multiply. Noticing that my 20s will cancel, negative over negative will now give me a positive 63 over 16 is my final answer. You can always do this work in the calculator too if you are fine with that. Just keep in mind that you might get really big numbers. And if you do, just go to the math button. Go over on the top of the screen to frac. Actually, no, not over to the screen. Sorry, guys. You're going to do math button and then choose frac down below and then hit enter. That will take whatever answer you have and simplify it down into its fractional part. Okay. Divided by 16 times 20. And we'll try that. Okay. All right. So the last part. Last part says verify the identity. All right. We're back to verifying all over again, just like we did in section 5.1, where we have to say the right side or the left side does in fact equal the right side. Okay. On question 1, we're using the sum identity. We need to prove that the left side does in fact equal sine of x. Well, they already tell us our alpha and our beta. So x is my alpha and 3 pi over 2 is my beta. It's a little bit different than what we're used to, but just watch. We're just verifying. The fact that they set this up for us already is just perfect in our heads. All right. So looking at my sum identity for my cosine, I want to do cosine of x times cosine of 3 pi over 2. Doing the sum, so that's going to tell me to subtract sine of x times sine 3 pi over 2. Now when I get to the parts with the x's, There's nothing I can do. I don't know what cosine of x is, so I'm just going to bring it down. However, I do know what cosine at 3 pi is, and I know what sine at 3 pi over 2 is. Forgot the denominator of 2, okay? Cosine at 3 pi over 2 is a 0. Notice what's going to happen there. And then sine at 3 pi over 2 is a negative 1. All right. Simplify there. Well, cosine times 0 is just going to cancel that out. Negative sine x times negative 1 is now going to give me a positive sine x. And there you have it. You just verified that it does in fact equal a positive sine x. All right, I'll let you guys try the second one here. If you want to get a head start, go ahead and try it. You have my teacher notes. I will go through this as well. This is another sum identity. This time, x is my alpha, pi is my beta. And I'm doing tangent. So I'm doing tangent of x. I guess I'll fill this in first. Tangent of alpha plus tangent beta divided by 1 minus tangent alpha, tangent beta. And I need to prove that it does in fact equal just tangent x. So I'm going to swap out what I know. 1 minus tangent x times tangent pi. Tangent x I don't know anything about yet, so I'm going to leave that there. Plus tangent at pi. Tangent at pi is going to be just 0 divided by 1 minus tangent x. Again, tangent at pi is another 0. So the zeros are going to go away, and they're going to make that into a 0. So the only thing I'm left with is just tangent x over 1, which is still, in fact, tangent x. And I have verified it. Right? So you have your sum and difference identities. They are officially discussed, and we have them on our golden ticket. So you always have these formulas. Key takeaways, again, always match the parts. If you're doing the sum, make sure you're taking everything on the top throughout the formula. If you're doing the difference, make sure you're taking everything on the bottom of the formula. Okay. Also, keep practicing your unit circle. It is not going away. Okay. You don't get it on your test, so we